Hey everyone, it's Mr. Canfield. Today we're doing the average value and second fundamental theorem of calculus. So these are essentially two formulas that we can see on the AP test. So let's just kind of go through. I'm going to go as fast as I can, and we're at a point where I'm probably just going to use my calculator for integrals. And I'm probably going to let you use your calculator for integrals. So integrals are a big deal. You know, we spent a long time doing them by hand, but I care a lot about concepts now, and we are trying to go quickly. So you might remember there is, let's see. So you might remember there's this theorem called the mean value theorem, and the idea was like if we had some kind of curve like this, and we looked at the average rate of change over an interval. So we called this mean value theorem. So this is just a little review for you to kind of get us started here. So if I'm looking like from here to here, so we call this A, we call this B. The mean value theorem said that average rate of change, so remember our average rate of change was this is regular f, sorry, f of b minus f of a over b minus a, right? This was our slope, right? Average rate of change, it's the same as the slope formula. And that mean value theorem said that this is actually equal to f prime somewhere on there. And we used the number c, the letter c. So that idea was like, hey, if I look there, that means that somewhere on here would be a tangent line, and sure enough, it's like right about there. There's some tangent line or some value c, sorry, where f prime of c is the same slope. It's exactly the same number as that average rate of change. And we had some necessary like things that had to happen. The first thing was our function had to be continuous and our function had to be differentiable. As long as our function is continuous and differentiable, so f needs to be continuous and differentiable. So as long as it's continuous and differentiable, we're guaranteed there's some, and the thing is, it's at least once. It could be multiple times. Okay, so that was the mean value theorem. So the mean value theorem for integrals, and I'm just going to use the pictures that he has here because these are really good. So we have some interval, so this one's going from 0 to 2, and there is some rectangle that we can make. So from 0 to 2, f of x dx, this is our integral, this is our exact area. We have this rectangle is less, right? That has less area, that has more area. Well, there's some place where if we pick a very specific x value, this happens at least once, the area of this rectangle and the area of our original thing, these are identical areas. So, and if you think about it, it kind of makes sense. Like if you start all the way over here at the left and make that rectangle, or you start all the way over here at the right and make that rectangle, you know, we have kind of at least with this one, we have the two extreme versions of what the area could be for a rectangle. If one of those areas is less and one of those areas is more, well, of course, there's going to be some point, and we don't necessarily know what it is, but of course there's some point where the area of this box is going to be identical to that area, because every possible area between these two happens as I go along this continuous curve. So all you need for this, if I remember correctly, is a continuous curve. Yep. So the curve actually doesn't have to be differentiable. It can have stupid little jagged points on it and stuff, but you're going to have a low area, a high area, and the area you want is going to be somewhere between the two values. So the math speak for this is if f is continuous on the closed interval from a to b, and this is a closed interval, that's why it's got the brackets, there exists a number c, and we could even say there exists at least one number c on a to b such that the integral is equal to, now this looks kind of weird, f of c times b minus a, but let's think about that. F of c is the y value, right? That's the height of the rectangle, and b minus a is like the end minus the beginning, so that's the base of the rectangle. So we can say that the integral from a to b is the same as the rectangle from a to b with the height like at that place that we don't necessarily know that place. It just happens to be there for this one. So let's see if he says anything more than me. What this says is that the area under the curve f of x between a and b can be expressed as the area of a rectangle with base b minus a times the height of the rectangle at some point c comma f of c. So basically what I was saying. And then we have, this is the real formula that we're going to use a lot. This is called the average value formula. This is not the way I'm used to writing it. I'll write it the way that I'm used to writing it. But we'll kind of talk about it. So we know average rate of change, right, is f of b minus f of a over b minus a. I'm going to derive a formula right now. You are not required to memorize this derivation or anything. But so average rate of change. Well, rate of change, we normally call that f prime, right? So if we want average f prime, we use f. What if we wanted average value? Meaning, what if we wanted the average of just plain f of x? We can use this formula again, this same idea, just instead of using f of x, instead of using f prime, we're thinking about f of x. So what I could do is, well, how did I get from f prime to f? I integrated. Or I got from here to here by taking the derivative. So if I want average value, I take the derivative of something and I get f of x. The thing that we took the derivative of is big F. And this is our average value formula. But we make it fancy by instead of saying f of b minus f of a, big F's there, we say that's the integral from a to b of f of x dx, right? And then instead of putting it all over b minus a, if you put 1 over b minus a out front, at least for me, that feels a little better than the way that Stu shows it. He has the integral on top and the b minus a on the bottom. But this, his version, this version, and this version, literally exactly the same. There is no difference mechanically between them. It might just help you think about it more accurately. So if we want the average value of f of x from 0 to 2 of this function, like literally, these are hey, plug in the formula problem. So f of x is x squared plus 1. Our interval is 0 to 2. If we want the average value, which I can't spell right now. Glad I didn't finish that. That would have been inappropriate. Not on purpose. So it's literally 1 over 2 minus 0. Then you go from 0 to 2. And then x squared plus 1 dx. Yes, this is an integral we can do by hand. No, I don't care if you do. I'm more interested in getting through this quickly. So I'm all about us going to our calculators and just typing it in. So what I'm going to do is I'm going to do the integral first. Oops. Oops, oh no, oh. That's no good. All right, this is taking me forever because I'm typing it wrong. 0 to 2 of x squared. There we go. Plus 1. So I'm taking the integral and then I'm going to multiply it by 1/2. Or I guess I'll divide it by 2. That'll be easier. So I got 2.3 repeating. I'll change it into a fraction because my calculator can. 7/3. So I got exactly 7/3. So 7/3 is the average value. And what that means is if you looked at all of the y values that happen from 0 to 2, if you look at all the y values, there's an infinite number of y values. But if you looked at all those y values and averaged them, you would get 7/3 exactly. It's honestly kind of a crazy result, but it's true and it works. So find the value of c guaranteed by the mean value theorem for integrals. So mean value theorem for integrals says, and this is where, so this was a formula. These are both formula. You want those formulas. You need to have those formulas memorized the day of the AP test. No real options there. Mean value theorem for integrals is very, very similar to average value in its formula. So mean value theorem says go from a to b of f of x dx, and that's going to be equal to f of c times b minus a. So it actually looks, it's like this, it's just this is going to be an unknown and this is going to be moved over here. So it's going to be from 0 to 2 of x squared plus 1 dx, and that's going to be equal to some f of c times, wait, b minus a. B minus a is 2 minus 0, which is just 2. And so if we're trying to find f of c, we'll divide, or wait, we're going to do this, right? And we're going to get 7/3. So when does f of c equal 7/3? Well, so that means that we're going to need to go to our graph and we're going to need to find out, hey, when does this, okay, you don't even need to go to your graph, right? We're trying to find c, and we know that x squared plus 1 is equal to f of x. So 7/3 is equal to x squared plus 1. So we just got to subtract 1 from both sides. So that's 3/3. So it's going to be 4/3 left. And then we take the square root. And it's got to be on 0 to 2, right? So it could be the positive or negative square root, but since we're on 0 to 2, we know it's the positive square root. So 2 over root 3 is going to be our x value that makes this work. So that's going to be our c value. All right. For example 2, I'm skipping it. It is literally the same thing. You literally use the formula. Well, okay, fine, I'll set it up. What you should do, you should try to set number 2 up without me if you haven't already. And then check, see if we have the same setups. So that's my setup. We'll get some number, and then for part B, if we're trying to find the place where it actually works, then we'll take whatever that number was and we'll set it equal to sine of x, to the original f of x, and we'll solve that. And we just want to make sure that our answer needs to be on 0 to pi. And Stu's answers are in the book, so you can go and check if you need to. But this is how we walk through this problem. You don't need me to do that for you. You are capable. But, you know, if you get stuck, you know where to find me. All right, part number 3. How long is this chapter? Good, okay. Part number 3 says, the velocity of a particle moving along the x-axis is given by blah. What is the average velocity of the particle from this to this? Now the average velocity, okay. Average velocity, ooh, I just underlined that. You might say, ooh, that's average rate of change, but this is our function, right? Whenever we want an average, so like, if I want average f of x, what do I use? In our formula, we use big F, right? If we wanted average, man, I can't spell the word average today. If we wanted average f prime, then average rate of change. If I want average prime, average rate of change, well then I'm going to be using plain f of x. So test yourself real quick. What if I said, hey, what's the average quadruple derivative? Maeve, I know. Quadruple derivative is a little extra. But our formula, we would use triple primes. So whenever we want the average rate of change or average value, average something over an interval, we always use the integral of whatever it is. We use the antiderivative of it for the formula. So that means if we want an average velocity, if I want average velocity, then I need position. So that means, well, if we want the average velocity, another way to say this is we want the average value of velocity. T equals 1 to e. So 1 to e. Something is shaking. I hope you guys can't hear that. So average value of velocity. So we have our velocity, so we'll take the integral of it and then go from there to there. Plug that into your calculator, that gives us the average value. And this is 100% doable with U substitution. It's a nice straightforward problem. It works out really well. But again, I am, in the interest of moving forward quickly, I'm gonna skip that. Because I care about you being able to set this up. We've already talked about how to solve integrals like that. All right, 4, table problem. All right, last time I had a table problem, I had to reshoot the video. The number of people waiting in line to enter Las Vegas buffet between 7 p.m. and 8 p.m. is shown in the table below. What is the average length of the line as approximated by the trapezoidal rule? Okay. So if we want the average length, now here's the thing, like the one thing to be careful of here is it says trapezoidal rule, so we're gonna do a trapezoidal sum. The only thing is it says average length of the line. So then that means we use our average value formula. Our average value formula says 1 over b minus a. So here's 8 minus 7 o'clock, but it looks like if we're going in minutes, right, it's gonna be 60 minutes. So you say 60 minus 0 minutes, go from 0 to 60 of people of t dt. you know, or whatever the heck you want to call it. But the trick here is that we have 1 over 60 out front because we're taking the average. And if I want to do a trapezoidal rule, remember that trapezoidal rule says 1/2, add the two bases together, which is the two y values, and then multiply by the height. And the height here is, let's see, 0 to 5, that's 5 minutes. Plus 1/2, take our two bases, and you might be like, instead of doing each of these by half, put the 1/2 out front, make it 1 over 120, perfect. So let's see, 1/2, two y values, 25 and 40. Now my height this time is not 5. I go from 5 to 15, that's 10 minutes. Next one is going to be 15 minutes, and it's going to be 40 plus 30. And my height is what, 15. Then 30 and 30. My height this time is 10, because 30 to 40 is 10 minutes. Then I got 5 minutes next. I got 30 and 25. 5 minutes. And then 45 to 55 is, let's see, 25 plus 20, adding our y values, and 45 to 55 is 10 more minutes. Then our last one goes 20 and 5 for 5 minutes. Do all that, hit enter, you're done. On the AP exam, I'm sure it would be a multiple choice question. And one of the answers they would give you, they would forget the 1 over 60. Because we see trapezoidal rule and we go, oh, I'm just going to do the integral. But remember, you do the integral, and since it's asking for average, then you have to make sure you apply the average value theorem thing. Okay. All right. I am actually going to cut the video there. Maeve is getting talky, and this last part deserves its own video. So, kind of sound like Maeve said, bye, and I'm going to say, bye.